Okay, so welcome to this third session of the Masterclass with Min. So it's actually no longer only a Masterclass with Min, because today we will have a talk from Montpellier. So it's organized by the Fédération Oxymat, so between Montpellier and Perpignan. So today's the first talk is as in the previous sessions given here in Toulouse, and then the second talk will be given from Montpellier. And the first talk is given by Xavier Lamy, and he's going to ask the following question: what does it take to deform an elastic body?
C'est pas son truc là? Okay. Well, thank you very much. I'm sorry I was late. Okay, so this is my title, and what you are probably not really going to learn from my talk is how to deform an elastic body, but it's just an excuse to talk about some mathematics. And the kind of mathematical objects that we are going to see are differential inclusions, PDEs, partial differential equations, calculus of variations, stability estimates. Those are some buzzwords of the mathematics that are behind the physics I will very briefly explain. Okay, so let's start from how we represent mathematically the deformation of an elastic solid. So just we have a domain in Rn. You can think n equals 2 or 3. And you have a map from your initial configuration to the deformed configuration. Okay? And you can think that this map U, it takes every molecule of your solid on the left to the deformed configuration on the right. Okay, why not? Very basic representation. Okay, and okay, so what we want to do is associate to such a deformation an elastic energy cost. So we kind of postulate that the energy will look like some integral, like we are summing over all the particles that you have in your solid, an integral of something that depends only on how the deformation looks infinitesimally. That is, it looks like it's acting infinitesimally exactly through its differential matrix, or its gradient, if you want. Okay? So what I'm not telling you is how it depends on the matrix du. But let us just pause for a second and think about what kind of objects we are looking at. U is a map from a domain in Rn into Rn. And so this du, it's a n by n matrix, right? Where you put all the partial derivatives of the vector u. And this w, it's going to give you, so the energy density is going to give you some non-negative value, and it's defined on all matrices, all square matrices. Okay, so that's the setting. So before we go a bit further, we will try to understand what this w should look like. And so we postulated that the energy will depend only on the gradient of u through such a formula, and now we want to understand, okay, what kind of properties this w should have. And one easy thing you can say is, okay, let's look at a very specific case of deformation. You take an affine deformation. So you just translate your body. This is for free. I mean, this will not cost elastic energy. You are not deforming the body. And now you apply maybe some stretches in some directions, things like that. And in that case, well, the energy is just, you can forget the integral, right? You're just integrating a constant. So the energy is just W of your matrix A. And what you expect is that the energy should be 0 if and only if I am not stretching or compressing the body, right? And the only things that do that are rotations. So really what you expect is that when you take an affine deformation, then the configurations that have 0 energy, where you don't have an elastic cost, they should correspond to affine deformations with the affine part is a rotation. And those are called rigid motions in classical mechanics. Okay, so this is very basic. And just by looking at this, you understand that your function w, which was a non-negative function, you know exactly where it vanishes, right? On matrices that are rotations. Okay. So Okay, let's give some examples of functions that satisfy that. For instance, you could take the distance of a matrix A to rotations and you square it. Why not? Or you could take things that are a little bit more complicated, like you take A transpose, you multiply it with A minus the identity, and then something that forces the determinant to be 1. Well, this is also a non-negative function, and if it is 0, then A transpose A is the identity, the determinant is 1, so you have a rotation. And you could also do something else. You could say that condition that A transpose A equals identity, it's actually the same thing as saying that A is equal to its cofactor matrix. Okay? So a cofactor matrix, maybe, hopefully you recall what it is. There is a definition. It is a sign times determinant of a submatrix. But the important property here is that when you take cofactor of A transpose times A, you get determinant of A times the identity. So again, this W of A, the third one, it will also vanish exactly when A is a rotation. Okay, so this is like basic linear algebra and differential calculus. And during the whole talk, you can think that W of A is the first one. And actually, all the other ones, they have very similar properties. And of course, you take specific physical material. This will not be the W of A. This is an oversimplification that I'm taking just for the purpose of doing some mathematics with it. Okay. Now, mostly the question I will try to understand in this talk is if I am able to describe deformations, so maps U, which have very small energy. Okay. Then first question is what I called rigidity, is I start looking at deformations that have zero energy, right? Very small, the first very small is 0, exactly 0. And what I expect is that the only configurations that should have 0 energy should be rigid motions, right? But remember, we have showed this already, we have shown this, but only in the case when U is affine, right? And it's not completely obvious that this will be true in general. This is something we need to check, otherwise the model, it has no interest at all. So I will spend quite a lot of time explaining that this is actually true. And then once we understand this, there will be, yeah, if you have to do that every time. Once we understand the rigidity, so I will explain that this rigidity question, it's not such a trivial one, and it's related to many other questions, and I will spend really a lot of time on it. And then I will spend the end of the talk talking about stability, which is the actual physically relevant questions, because in real life, there is nothing that is ever exactly 0. There is always a little bit of noise, right? And so what's really important is not to understand this, is to understand if I have very small energy, can I say that U is very close to a rigid motion? Okay, rigid motion again is just translation and rotation, something very simple. So this is the program. Okay. Now I want to do a rephrasing of these questions in terms of mathematical objects that are differential inclusions. Okay, so here I have a set K, I call it K, which are just the rotations in A by N matrices. And I can rephrase my two questions in the following way. The first one is, if I know that the matrix du is in K at every point, can I deduce that actually du is a constant? Because this is really what we are asking here. Show that the map U is affine, which means that du is a constant. So I'm hoping that our set K, it has exactly that property. And then the second question is, if I know that the distance, that du is not in K, but it's in K up to a very small error, and small is in this sense of the integral of the square is 0, is small, then can I deduce that du is very close to a single rigid motion? Okay. So I will come back to the stability later, but first let's concentrate on rigidity. And let me give you a few examples of other differential inclusions that are interesting in mathematics, so that you have a feeling of the kind of stuff that could happen here. So first, if I take 2 by 2 matrices, so I'm thinking maps from R2 into R2, and my set K, I take the rotations times a number, so rotation times the homothéty. Well, actually, you know the objects that are solutions of this differential inclusion, because a rotation times the homothéty is exactly multiplication by a complex number. Okay, so those are exactly the holomorphic functions when you identify R2 with C. Okay, so this differential inclusion, you can rephrase it as just the Cauchy-Riemann equations if you want, or the fact that U is holomorphic. Well, in particular, you see that U is not at all affine, right? It can be much more complicated than affine. So in that sense, we don't have rigidity like we're asking for rotations. Let me give a second example. If you take the set of symmetric matrices in any dimension, so you are asking about maps U from Rn into Rn, so that the Jacobian matrix is symmetric. Well, you know that if U is a gradient, this will be true, because the Jacobian will be the Hessian of V, and so it will be symmetric under some good regularity assumptions. And in fact, if the domain omega has good topological properties, this is an equivalence. This is called the Poincaré's lemma. So the solutions of that differential inclusion, we can also all classify them, and those are just the gradients. In particular, you have a lot more solutions than just affine functions. So it was kind of obvious that, I mean, if K is very large, then there is no hope that I will get this. But I mean, okay, those are examples of differential inclusions where you can ask also other types of questions, and I will not go further into that. But in those cases, you have no rigidity, so we really need to use something very specific about the set K, right? Okay, so now let us go back to our set K, which are just the rotations. And the theorem that states that there is rigidity is due to Liouville. It was proved in the middle of the 19th century. So this is very old mathematics I'm talking about here. And what Liouville proved essentially is that if U is a C2 function, a C2 map, actually twice differentiable is enough, and is differential everywhere is a rotation, then in fact U must be affine, so it is just a single rotation. And as we have seen, I mean, this is not something completely trivial a priori. I'm saying that du belongs to a certain infinite set, and at the end I realize it's just a point, this du, in that set. So I'm going to do the details of the proof, exactly the same proof that Liouville did a long time ago. The proof is like that. Well, what does it mean that du is a rotation? It means that its columns, they are orthonormal vectors, right? And so I'm writing that diu scalar dju is just d delta ij, it's equal to 1 or 0. Okay. Actually, I won't care that it's 1 or 0, I just care that it's something that does not depend on x. Now I take a derivative of this relationship. So you see, I take a derivative with respect to k, the k's variable, and I get that diku dot dju plus diu dot djku is equal to 0, just product rule. Very easy. Okay, let me give a name to this thing aijk, which is diu dot d squared jku. What we don't see here anymore is that this identity that we obtained when we differentiated this with respect to the k's variable, it's really saying that aijk is equal to minus ajik. But now if I also use that the Hessian of U is a symmetric matrix, then in fact I can also inverse the two last indices. You see the aijk, it's completely symmetric with respect to permutation of j and k, just because of the fact that the Hessian is symmetric. And now when I write it like that, what do I see? You see, when I go from indices I, j, k to indices j, k, I have multiplied a by minus 1. Okay. But this is a cycle, you know, okay? So I've just shifted everything to the right. And so if I apply it 3 times, I come back to the identity. But what does it mean? I apply it 3 times. I multiply by minus 1 again, and minus 1. So at the end, I have multiplied by minus 1. And I've come back to the identity in the indices, so I realize that this aijk is actually equal to minus itself. So it's actually 0, okay? It is actually 0, so the fact that aijk is 0, this is what's written up there. But now if you recall that diu, it forms the basis of Rn, you realize that this is telling you that actually the Hessian must be 0. Okay? So you conclude that the Hessian is 0 everywhere, and so u must be affine. Okay, du must be a constant. Okay. So, I mean, you have to be a bit astute in using these cycles, but it's quite elementary. Okay. So, conclusion, just let me state again that conclusion, and there is a misprint here, there is a typo. What we just showed is that if the energy of u is 0, there's equals 0 missing, then u must be affine and it must be a rigid motion. Okay. Of course, we use the condition. We use that we had 2 derivatives and that the derivatives of order 2, they commuted. Okay. So I say C2, it's enough to say twice differentiable, but we used a lot of regularity in some sense, 2 derivatives, right? So it's kind of, in some sense, disappointing that we had to use second derivatives, because really the energy, it makes sense without second derivatives, right? I can think of that energy with a map U that is just differentiable, even almost everywhere, okay? So the question that is natural to ask is this implication, is it still true if U is actually less regular? Okay. There are many ways of proving that this implication is true if U is less regular. I'm going to explain one way that is not the easiest one, but because I want to introduce some objects that have some that are interesting for themselves. Okay, so the question we have shown, if U is twice differentiable and its differential is everywhere a rotation, then U must itself be a rotation, basically. And now we want to remove the assumption twice differentiable. We want to do it just for once differentiable. Okay, so I want to go down a complicated road to remove that assumption, but it's because I think it's fun. So first, let me do a small remark. I take any twice differentiable function. I take its cofactor matrix, and I take the divergence of each of its rows. So if you don't know what divergence is, well, this is this formula here. dj cofactor du ij is equal to 0. And when you see the same index here, j repeated twice, you have to think that there is a sum over it. This is a convention. Okay, so this is just, okay, the cofactor matrix, it has a definition. Okay, you can look at its explicit definition. You can do the calculation. You have some second derivatives, you use Schwarz's lemma, and at the end, trust me, you have to trust me here, you see that this is 0. Okay? Okay, what does it have to do with anything? Well, if I add my assumption that I had in the beginning, that the Jacobian matrix is a rotation, then in fact the cofactor is just du itself. Okay? So if I use that in that equation, I say that cofactor du is just du. Then what I end up with is a PDE that is quite simple, actually. So it's a very important PDE, so it has its own symbol. It's the Laplacian of u equal to 0. If you don't know what the Laplacian is, where it's just you take the sum of all the second derivatives in all directions. Okay? And again, this is just a direct calculation. You calculate the divergence of the rows of each of this du, and you get exactly the Laplacian. Okay. So u is a harmonic function. So functions that have 0 Laplacian, they are called harmonic. And perhaps you know, or at least it's a result, that harmonic functions, they are very, very regular somehow. Okay, but this is completely stupid what I just did. Of course, we know it's harmonic. I assume it is C2. I know it is affine, so it is harmonic. This was completely useless. Well, not that useless. Let me go a little bit more into detail. The whole point is that actually there is a very nice way that probably many of you know to make sense of these calculations I did, even if U does not have second derivatives in a classical sense. Okay. And you see, we started from this identity which was kind of magical, divergence of cofactor of du equals 0. Okay, and the first thing I want to do in order to explain where this other way, this weak way of making sense of all this comes from is to give a physical interpretation for that identity. So let me start from looking at one quantity, which is the volume of my deformed solid. Okay, it has some volume, and the volume, maybe it's not surprising that it's exactly the integral of the determinant of du. Okay, so here I'm cheating a little bit. Maybe U is not a diffeomorphism or things like that, so I have to be careful about what I mean by volume. But let us just assume, for the sake of this talk, that this formula really represents the volume inside the image of U. Okay? Then there is a very simple thing that one can say about the volume. So I write clearly, because it's intuitive. Really, it would require a proof, which I'm not going to do. But somehow, okay, the volume inside this, it really depends only on the boundary of this, right? If I know the boundary, I know what's inside, I know the volume. Okay? So if I change my map U just inside, not at the boundary, this should not change the value of the volume. Okay, so this is what I write here. If I take another function, which also takes values into Rn, so I can add it to U, but is 0 at the boundary of omega, then I'm not changing the boundary of U, so I'm not changing the size of the volume. Okay, this you have to believe me, it's actually a short calculation to prove it, but for now, let's rely on the physical intuition that the volume just depends on what's on the boundary of it. Well, then you come to the whole idea of calculus of variation, which is, okay, now let's take variation with respect to that phi. What does it mean? Okay, if it's true for all phi, I can also multiply by a number t, and then I can take derivative with respect to t. Well, if that function is a constant with respect to t, the derivative is 0. Okay, so let's look at what happens when I calculate this derivative. Okay, so I calculate the derivative at t equals 0. I have enough assumptions that I have to make actually to let the integral and the derivative commute. So I put my derivative inside, and now I'm derivating this thing, determinant of du plus t d phi. At t equals 0, what do I get? I get the differential of the determinant at the point at the matrix du applied to the matrix d phi. Okay. Now you recall that this was an exercise in your differential calculus course to actually calculate the differential of the determinant. And okay, there are many ways of doing that, but you can say that actually the differential of the determinant, its partial derivatives are exactly the coefficient of the cofactor. Okay, it's like a direct consequence of this formula for expanding the determinant with respect to columns and lines. So actually here, this differential of the determinant, I'm going to be able to replace it with something with the cofactor. So we see that I'm getting closer to something that I told you about before. So again, I plug this into that, and I get that this whole derivative, which was supposed to be 0 because it was the derivative of a constant function, is actually equal to that. So the cofactor matrix at du, it's ij component times dj phi I. And here you see that I and j, they are both repeated, so I'm taking sums here. I'm taking sums over I and j. The sum is not written, but it's there. Okay, Now let's look at this quantity and assume again that, so far I've never used second derivatives of u. Now let me go back to using them, and I assume I am C2, and I do an integration by parts. Okay, you see this dj phi I want to put it on the other thing. And because phi I has compact support, there are no boundary terms. I can just do the integration by parts, and when I do that, what do I get? I get the divergence of the cofactor of du. Okay, so basically I'm saying the divergence of the cofactor of du integrated against any function with compact support is 0. So you see, we are not surprised because I told you that the divergence of the cofactor of du is 0. This is an identity, and in some sense, this is a proof of that fact. A proof that relies on that interpretation with the volume depending only on the boundary. But also what we have learned is that somehow this identity is the same thing as this, and here we don't need second derivatives. So let's take this as the definition of this. Okay, so if u is not a C2 function, if it does not have second derivative, then somehow asking that this cofactor du integrated against the differential of phi is 0 for all phi with compact support, this is a weak way of saying that the divergence of cofactor du equals 0. So of course many of you have started to learn theory of distributions, so they realize that what I'm doing here is just weak derivatives in the theory of distributions. But what I find interesting in this calculation is that not only it gives you this weak way of thinking about derivatives, but in fact it's really the actual physical way to think about it, because we get it from the physical information that the volume depends only on its boundary, right? So in fact this is not the right way to look at this. The right way to look at this is this one, okay? So this is not the weak way, this is the good way. One point I want to make, that distributions, it's not only just a mathematical way of making sense of weird stuff, it's actually the way it comes from physics. Okay, so now the good news is this equation, it makes sense even if u only has first order derivatives. Okay, even if u is just differentiable, we understand what this means to be a solution of this equation. And now if you also add the condition that du is a rotation, then you put it in here and it becomes Laplacian of u equals 0 in a weak way. Okay, again integrated against some test functions. Now there is a theorem that I'm not going to show you, but if you take a u that is just differentiable, even it does not even need to be differentiable, and if it satisfies that the Laplacian is 0 in that weak way that we just talked about, then actually it has to be smooth. Okay, so it is actually not so hard to show in that simplified context. I'm not going to tell it to you to show you. Maybe you have already seen it in some classes. It's called basically elliptic regularity theory, except it's just a very simple case here. But my point is, now that we have this PDE, Laplace u equals 0, we know automatically that u is as smooth as we want. So we are in a situation where we can apply Liouville's theorem that worked when we had second derivatives, right? And we realized that the implication that was shown by Liouville, that if du is a rotation at every point, then u has to be affine. It looked like we needed to know in advance that u is smooth, but in fact, no. From that result, we can just deduce that u is smooth just from that information. Okay, so here I'm cheating. I'm writing it is true also if u is just differentiable. It's not completely true because I have to justify all the things that I did of letting the derivative and integral commute, etc. So just differentiable would not be the right thing, but if you assume that it's differentiable and the differential is bounded, for instance, then you can make sense of everything. And the point I wanted to make here is that using the fact that behind this differential inclusion there was a PDE, this partial differential equation Laplace u equals 0, we obtain some regularity, and once we have regularity, we can make all the calculations we want. We can apply Liouville's proof, and we deduce that exactly what we wanted, that when the energy makes sense, and it is 0, then u is a rigid motion. Okay, and here I recall that the energy is the integral of distance squared of du to rotations. Okay, so this really completely settles the question of rigidity, and basically it was done in the 19th century, and you just need to be a bit careful to say that you don't need so many derivatives on u. Are there questions so far? Okay. So we could say, okay, but this whole business about it worked for C2 and we have to make it work also when we have less derivative. I mean, it worked. So maybe there is a theorem that says it will always work. I'm telling you that here I'm claiming that no, it's not the case. Sometimes you have differential inclusions that are rigid for C2 maps in the sense that I just said, but they would not be for C1 maps. Okay, so this is to say that this extra work that we had to do after Liouville, it was not just some trivial thing. It's something that we could really have had problems with, and here the fact that we were dealing with this special set of rotations actually was important. I'm not going to give you the very explicit example, but maybe you will know what those words mean. So an example of that thing is the question of existence of an isometric embedding of the flat torus into R3. So the flat torus, this is just the square where you identify the sides. So if you're allowed to deform it, then you know it's this kind of really an actual torus that looks like a donut like you put in R3. So putting the flat torus into R3, it's really like deforming it into a donut. Now imagine you're not allowed to deform it. Well, it looks like you cannot do that. And the reason why you cannot do that is because if you have, so this being an isometric embedding, I'm not telling you the definition, but it's really a differential inclusion, okay? And that differential inclusion is rigid in the sense that the flat torus is flat, its image, it has to be flat, okay? And so you will never get your donut that cannot be flat. But what Nash discovered and then Gromov built upon it, and then many people use these ideas, is that in fact, if you just ask that the isometric embedding be C1 instead of C2, then you cannot talk about curvature anymore. So you cannot say the image has to be flat. And in fact, it is possible to construct solutions that are really not flat. Okay. So this is, okay, if this was maybe a bit complicated and you don't know what I'm talking about, but the point I wanted to make is sometimes it doesn't go as well as what we just saw. And actually the theory behind why does it not go as well is extremely rich, and many very strong people have worked on this, and it's still today, it's still giving a lot of information on many, many mathematical objects. So this kind of seemingly very simple question is actually a very rich question. End of the parenthesis. If it was too much, then you can come back. Okay, so now we come back to our initial question, which was about that energy, right? And we have shown that we have rigidity. If the integral of the distance of du to rotations is 0, then u must be rigid motion. In particular, it must be affine. Now, the question we ask is, if the energy is very small, must u be close to a specific affine function? Okay, this is kind of the next natural question. And as I said, this is in fact, this is the right question. This is the physical question, because nothing is ever 0 in the real world. So in some sense, the rigidity is completely worthless physically if you don't have this, if you don't have a stability that goes with it. Of course, okay, I wrote some things like very small, close to affine. So here there is a lot of room for how should I interpret this thing. Let me give you an answer that was given by F, J, and M. Those are the initials of the people who did it, Frieseke, James, and Müller, in 2001. So you see, more than 150 years after Liouville's theorem, people were still working on these questions and understanding new things about that. What does their theorem say? Okay, there is the energy of U. Because I think of it as being small, I call it epsilon squared. Okay. Then I can find a single rotation so that du, in some integral sense, is very close to that single rotation. Okay. So it's really exactly what we want. We want to say that U close to affine, it means du is very close to a single matrix. Okay? And this is exactly what that theorem is telling us, and this is the stability I was talking about. So there are, basically from the 1950s, a lot of good people have tried to understand questions of that type, in particular in the Russian school, and they have given different types of answer. This is just one that I select because I think it's nice. All right, so my goal for the end of the talk is to kind of understand what this is really saying and how we could prove this kind of facts. But first, as I did before, I mean, okay, this is going to work when we are looking at matrices of rotations. This is really something specific to rotations. In fact, if you take another type of differential inclusion, so here I'm not even giving you an example, I'm just claiming it. I claim that there exist differential inclusions that have the rigidity property, meaning that if you know that du is always in some sense that in fact u must be affine, du must be a constant, but which would not be stable in any reasonable sense. That you could have the distance of du to k that could be very small in some sense, but du would not be close to a constant. So this kind of pathological objects, they do exist. And physically, they are telling you something new. They are telling you that this question, somehow you did not understand the physics behind it, because really small energy configurations, they do something different. Okay. So I will really not enter at all into the details of such examples, but I just thought you should know that they exist. And somehow it makes that result here even more interesting, right? Because it means this is not something general. We have to understand why matrices of rotations are so particular. Okay, but again, this in general may work, but if I take K the matrices of rotations, it works. And here I just rewrote my stability estimate that I wrote in the previous slide. So again, let us look at it. This thing that I had called epsilon squared, now I just exactly give its formula. So we are saying that if I take any map U from omega into Rn, then I can find a rotation so that the integral of du minus r squared is less than the energy, basically.
You don't even need these quantities to be small.
So in some sense, this statement is void if the right-hand side is not small. So it's really just interesting when these quantities are small. And in particular, it's telling you if the right-hand side is small, then the left-hand side would be small. And this is the interesting regime. But it's true in general, so we can write it like that. Okay, this is the proof is really nice, and I want to give some ideas. Basically, it relies on two steps. First, the first step is to obtain an infinitesimal version of this inequality. So what does it mean, an infinitesimal? Okay, let me start from a map U that is already close to a single rotation, say the identity, okay, the most simple of rotations. And now I take it, the identity plus something, and that something is very small. Okay. You see, I even wrote it with a small parameter t here. Now what I can do, I want to have this inequality. I can say, okay, let me do the expansion of both sides, the Taylor expansion in powers of t. And then I will look at the Taylor expansions on both sides, and it will give me some inequalities that must be satisfied when I let t go to 0. Okay, let's do that. Well, actually, I'm not going to do it, but I'm going to give the result. If you do that, then you see that the first non-trivial terms that appear will be on the left just the integral of gradient of phi squared, because the r I'm going to take is just the identity. So it's clear that du minus identity is going to give me something, t squared times integral of gradient phi squared. And what will appear on the right is this thing here, the integral of the square of the symmetric part of the Jacobian matrix of phi. So okay, one can do the calculation and see that this works. Let me just give a rough intuition of why it's like that. Well, you look at matrices of rotations as a subset of square matrices, and you want to take deformations tangent to it. Okay, so maybe you know that the matrices of rotations is a very nice smooth set, and that its tangent plane is actually the set of antisymmetric matrices. Okay, some might call it even the Lie algebra of that group. So anyway, here I'm saying my right-hand side, the only thing it's saying is that the distance to the matrices of rotations, if I look very closely, I zoom in close to the identity, it looks like the distance to the tangent plane at the matrices of rotation. So the distance to antisymmetric matrices. And you see, this is exactly what this is doing. The right-hand side, it is 0 exactly when the matrix is antisymmetric. Okay? So really, the right-hand side, it is the distance to the tangent plane at the identity of this set. So when you view things like that, I mean, you realize that this inequality makes sense, and this should be really the one. And of course, if this inequality is true, then this must be true. I mean, this is a necessary condition because you plug your Taylor expansion into it, and then you must have this inequality that you see at first order. Okay? So not only we are going to use it in the proof, but in fact, I mean, we should check it's true. Otherwise, there is no hope that we are going to ever show that. So I'm going to spend some time explaining why this infinitesimal version is true. Let me just say a few words about once you have your infinitesimal version, how do you prove your full inequality? Well, in some sense, you can think of it as, okay, I want to prove inequality, so I want to prove that a single function is positive. Okay, I can write the inequality as a minus b larger than 0. I want to prove that a single function is positive. What did I do here? I checked that it is true up to order 2 locally. So I know that locally I have a point where the differential of that function is 0, and the second differential is positive. So I know that locally I look like something like x squared, and I'm positive, and there is a nice estimate. Okay. But this is only a Taylor expansion. This is only a local thing. So I need to actually control more precisely all the other terms from the Taylor expansion that I threw away when I did that. So this is why the second part is to control all the other terms, the ones that do not come from the beginning of the Taylor expansion. And actually, this was known for a very long time. And what those people, Frieseke, James Müller in 2001, what they improved is that second part. What they understood is that there was a very easy way of using. Remember, we used that equation before, that the Laplacian of u is the divergence of du. Okay, this is just the definition of the Laplacian, basically. And then before we were using that du was a rotation, so this was the same thing as the cofactor. Here we are not assuming that du is a rotation. But since we know that the divergence of the cofactor of any du is 0, we can just include it in here, right? And now what we see? We see that what we have inside the divergence is something that must be small if I am close to a rotation, right? It would be 0 if I am a rotation, and if I'm close to rotation, it's going to be small. So in some sense, the idea in that proof, and I'm not going to say more about that, is to use that PDE that we used before to improve Liouville's theorem. Before it was Laplace u equals 0, it gave us a lot of rigidity. Now it's Laplace u equals something small. Somehow it's helping to control all the other terms in the Taylor expansion. And really, I'm going to remain as vague as that, but just I wanted to tell you there are some very nice ideas related to PDEs that are used in the proof. Ok.
Est-ce que moi tu m'entends, Mathieu?
Oui.
Ah ouais, j'ai l'impression que c'est la batterie du truc qui est...
Ok, vous avez perdu le son il y a longtemps. Vous m'entendez là?
Non, juste la dernière 30 secondes. Là,
ah ok.
Tu voulais te parler de... En tout cas, tu avais fini d'écrire.
Ok. Okay, so now what I don't want to spend time on is this second step, the fact that there is a way to control the rest, and this is actually the contribution of these people in 2000 to use that PDA in a smart way in order to control the other terms in the Taylor expansion, basically. But okay. Now let me go back. I want to explain just why the infinitesimal version is true. So the infinitesimal version, it was known for a long time, and it actually has a name. It's called Korn's inequality. So this is again what I write here on the slide on the right. So again, what is it telling us? It's telling us the integral of grad phi squared is less than a constant times the integral of the squared of just the symmetric part of the Jacobian matrix of phi. Okay, so in some sense, what am I saying? The symmetric part of the Jacobian matrix, which is the object that appears on the right-hand side, it is enough to control completely the full Jacobian matrix. So if you think about it, I mean, this is something non-trivial, right? I'm saying that this smaller thing can control this thing that naively would not have been controllable by that because it contains a lot more information. So the question is, why can we even hope that such a thing is true, right? Why is that? Well, I'm going to give you one reason for that. I'm going to prove it in the case where I have basically no boundary. So I'm assuming that my map phi, it is defined in the whole space Rn, and it has compact support, so that all integrals will make sense, etc. And then I will do some Fourier analysis. So okay, I'm going to calculate this integral of the symmetric part squared. This is just the definition. Okay, the sums of all these di phi j plus dj phi I squared. Okay, just the definition of what the symmetric part is. And now let me write it in Fourier. Okay, you know you have in Fourier you have this Parseval identity, and you know that in Fourier space, so I call xi my Fourier variable. The di it becomes basically xi I, and the dj it becomes xi j. So in Fourier, I have an equality here. Maybe there is a constant depending on the convention you use for Fourier, but let's just assume the constant is 1. Okay, and now let's just expand the square. What do I have? I have xi I squared sum phi j squared plus xi j squared sum phi I squared, and then I have this mixed term. Okay, very elementary. Okay, so this I can rewrite actually. If you look at this, I have the xi I squared. The sum of this is just xi squared, okay, and the sum of the phi j squared is just phi squared, and I have this twice here. So the first two terms, when I do the sum, I find twice the Euclidean norm of xi squared times the Euclidean norm of phi hat squared, okay. And then I do the same thing with the mixed term that we don't see anymore, but basically you realize that it's also a square. And that's the whole point. You have something here plus a square. And a square is a positive number, okay? And so it's actually, you can forget about the last term, okay? This is certainly higher than the first term. And now when you have the first term, you're very happy because you come back to your original variable, and this is exactly the integral of the gradient squared, okay? So this works. I mean, somehow this was amazingly simple, even though the result at first it looked like something quite deep. And this gives you already Korn's inequality when there is no boundary. I'm in the full space. I'm allowed to do Fourier, etc. Okay, but it already gives you a hint of why you can expect that Korn's inequality is going to be true. And then if you want to prove it in a domain for any map, this is another story that I'm not going to go into right now, because I think I'm going to stop probably. Yeah, just give you some conclusion if I am allowed to take 2 more minutes. Okay. Well, anyway, the conclusion is just kind of a summary of what we did. So we were looking at one specific object that I called a differential inclusion, which is the condition that I have a map U and its differential belongs to some set. And we were looking all along, our motivating example was the set of rotations in A by N matrices, but what I explained at some times, or I pointed out, is that in fact all these properties that we found, it can be sometimes not true, sometimes you have to explain a little bit more what you mean. So these questions of rigidity and stability for these objects are very rich questions and still active questions of research. Another thing that I find interesting is really I started from Liouville theorem in 1950, and I told you about the theorem in the early 2000s, and in fact, I mean, on this first point, there are every day like theorems being proved about this kind of objects. So this is really, I mean, this thing that started in the 19th century, this is so rich that people are still working a lot on this. So we are spanning a long history of mathematics. Okay, and what we showed is that for the case of rotations, then we can show some very precise things. And I gave you some ideas about how to do that. And another thing that I find nice about it, and you saw there were many tools that came into play, right? There was this these PDEs, using the PDEs to help you get regularity. There was this idea of calculus of variation that when you have some identity, you can differentiate it and obtain some new identities, etc. And this is where I stop.
Thank you. Do you have questions? So here are Montpellier.
About the set K, you said that for some such K there is no stability. What kind of set, is there a way to characterize it?
A way to characterize it, what you can say is that if inside your set K you have certain configurations of matrices, it can be just only, you can even construct, I think, a set K with 4 matrices inside. And if they have very specific algebraic relationship between them, then you will be able to construct sequences of solutions that converge, the distance to that set converges to 0, but really the solution, the gradient of the solutions is very close to any of these things in some sense. Any of the 4 matrices, not concentrated near one. And if I want to get into more details, it will become very technical, and also I didn't rehearse that, so I won't be able to give you something really good.
Your FJM, I forget the names, your FJM theorem gives you an L2 stability. Did people do something in other, I suppose L infinity is impossible, right? Because you could perturb in a small set.
Right, so you see that...
Do you have other LPs?
Yeah, exactly. So you see one of the crucial points was to use that PDE, Laplace U equals something. And so when you say that this is the crucial point, what you expect is you will have estimates in LP as long as P is not 1 or infinity. And in fact, this is what, I mean, I don't think they write it, but really you take their proof and you can also do that using the same kind of proof. And of course, infinity and L1, probably you could find counterexamples. But I did not check that. But
Or maybe weak versions like...
yeah, probably you have to modify borderline spaces and yeah. But LP is easy with the same proof.
Okay.
And Calderon-Zygmunt estimates, of course.
Other questions? Mathieu, do you have questions in Montpellier?
Maybe they did not even hear me, so you're asking questions and stuff.
Okay, so if not, we can thank Xavier again. Thank you very much.